Good afternoon, everybody. Let's get started with the class. For announcements, so there's a teaching assistant feedback survey that's happening, and I sent out an announcement on Canvas about that. So if you have some time, fill out that survey. I think you have a few days to do that. Take a look at that. We would appreciate some feedback there. Pre-Lab 5 and Lab 5 will be this week, so that is posted on Canvas. My office hours will be right after class if you would like to join, so stop on by. So last time we finished up transient circuit analysis and we started talking about sinusoids and phasors. So we're going to continue talking about phasors and sinusoidal steady state analysis. And I started off just a little bit last time talking about what a phasor is. So a phasor represents the amplitude and the phase of a sinusoid. And it does this using a two-dimensional vector. We're going to use a complex number, as I'll show, to do that, and also define a phasor mathematically for you. So we use phasors to solve RLC circuits that have sinusoidal sources. And so you can have sinusoidal voltage sources and or sinusoidal current sources. Usually all of them are at the same frequency, but they have different amplitudes and phases. And so using phasors is an alternative to solving circuits using second order differential equations. Okay, so we'll have RLC circuits. Usually in general, those will wind up to be second order differential equations representing voltages and currents, but we're going to use phasors instead. So we use phasors to solve what we call sinusoidal steady state problems for linear circuits. So we'll have linear sources in these circuits. You could have controlled sources, but they will be linear. So in sinusoidal steady state, so this is different than the this is different than the steady state that we talked about a couple lectures ago. So a couple lectures ago for steady state, we turned on a DC source, or we had a DC source, and then there was a sudden change on the circuit. We flipped a switch, we plugged in a resistor, something like that. There was a sudden change, and then there was a transient response between some DC value and another DC value. Well, since we don't have DC sources here, we have sinusoidal sources. This is what sinusoidal steady state means. So all voltages and currents are sinusoids. So if you have sinusoidal sources, voltages or currents, then every current and every voltage throughout the circuit will be sinusoidal. And when we turn on these sinusoidal sources, we let the circuit settle a bit, but all amplitudes of all of the sinusoids throughout the circuit, voltage and current, will converge to constant values. So the voltages and currents are not constant, but the amplitudes of those sinusoidal voltages and current are steady. So if you have a 2 sine omega t, right, you have an amplitude of 2, it's not changing after a certain amount of time. And not only have all amplitudes converged to constant values, but all phases have also converged to constant values. Okay, so the phase and the amplitude are not changing. Okay, so I want to move over to the whiteboard and talk about this a little bit. I want to show you what we're going to do basically graphically, and then we'll move on to a mathematical definition of phasors. So let's switch over to whiteboard. Okay, we're going to go back a long way in your educational career. I'm going to go from about second or third grade to Euler's formula on one whiteboard, because I think it's important to be able to visualize what we're doing here. So remember number lines. If you can remember back to grade school. Number lines were a way for us to visualize a range of numbers and what we were doing. So we did this in one dimension, right? We had a 0 and we had 1 and we had 2 and we were learning how to add and subtract by moving back and forth on the number line. And then we included negative numbers, -1, -2, -3. And this let us visualize graphically or in space what it meant to have a negative number. That if you took 3 away from 2, you went to the negative side of 0 and you had -1, and that let us make sense of what it meant to be a negative number. But this is, I won't dwell on this, but this was one-dimensional space. Okay. And then sometime, I don't know, was it middle school or something like that, or late grade school? We moved to 2 dimensions, right? We added an axis to this number line and we created a number plane. We started out probably calling the horizontal axis the x-axis, the vertical axis the y-axis. We said, oh, we can have these numbers along the x-axis, even in the negative direction. We could have numbers along the y-axis. And now, not only could we represent a value in one-dimensional space, right? We were representing values in two-dimensional space, and we went to higher dimensions, but we'll stop here. So if I had a position in 2D space, right, we could label that x3 and y2, right? Something like that. And that would uniquely define some value on this two-dimensional plane, or this plane. Okay. And at some point we said, well, that could be a vector. That could be a vector that starts at the origin and ends at that point. And then we introduced vector notation. We could say, we could call that vector 3, 2, but we introduced unit vectors. And we said some vector v is equal to, well, 3 unit vectors in the x direction. Let's just call that 3ax. There's different ways to represent this, but ax hat is a unit vector in the x direction. Okay. And then we said, well, we're going to now express the y dimension with a y unit vector, ay hat, right? And that represented this vector of this length and of that orientation or that angle. Okay. And what this helped us do is when we added vectors to get a resultant, we would only add x components to x components and y components to y components. And so you would keep these components separately in 2 dimensions. And then we also then moved not only express these values or these points or these vectors on a 2-dimensional axis using Cartesian coordinates, we used polar coordinates, right? So we said, okay, this vector v, let's label this vector v here, has some length. We could call that length a. Okay, and we said we could also describe this vector with an angle, so that angle theta. And what that let us do is express this vector v like this: a at an angle of, there's a little angle symbol, theta, right? So that's polar coordinates. So here's rectangular or Cartesian coordinates or polar coordinates. Okay, and again, so what we could see here is that if we added vectors together, we would keep x and y components separate, and that we could express values in 2 different ways. We could express any point on this plane or any vector to any point on that plane in Cartesian or polar coordinates. Okay, so this is where we start talking about the amplitude and the phase of a sinusoid and relating that to points on a plane. I mentioned that we are going to not use unit vectors in X and Y. We're going to use complex numbers. Okay. And complex values, complex numbers, you could say in general have this form, A plus J B. Okay. And you say, what is that J? That J is the square root of -1. And you say, why is that J and not I? We use I in our physics and math classes. Why do we use J here? It's because we've already reserved I for the variable for current. Okay, so in electrical engineering, we typically use J instead of I to represent the square root of -1. And if you're like me, if you're like I am, this isn't very intuitive. So let me show you a more intuitive way to visualize complex numbers. Okay. Remember that when you add complex numbers, you add the real part, A is the real part. You add the imaginary parts, JB is the imaginary part. And you never add real to imaginary or imaginary to real. You treat the real part and the imaginary part separately when you add complex numbers, right? Well, that's just like adding two-dimensional vectors together. You would add the X components, you add the Y components, and that's your resultant vector, right? For complex numbers, you add the real parts together, you add the imaginary parts together, and you never mix the two. Okay. So there's this analogy or this representation where you can show complex numbers on a two-dimensional plot, which we call the complex plane. On the complex plane, we have two axes. We have a real axis, and we have an imaginary axis. Okay. And so let's suppose I have some complex number, A plus JB. And let's make that number 3 plus J2. Okay. Remember, J is the square root of -1. Some people might, in physics, write 3 plus 2I, right? It means the same thing. Oftentimes, I put the J first. You can put the J second. You can call this 2J or J2. Doesn't matter. I'm just used to putting the J up front so I can recognize the complex part of the number. But this complex number has a real part, 3, and an imaginary part, J2. And what you can do is represent this complex number just like we represented X and Y on the two-dimensional plane here. So 1, 2, 3. This is 3. So 3 along the real axis, right? That represents 3. And 2, J1, J2 along the imaginary axis, and that would put us right here on the complex plane. And oftentimes we express a vector with a complex number like this. And remember that if you're adding vectors, you add the X components, you add the Y components. So adding complex numbers is just like that. You add the reals, you add the imaginaries. Okay. So you can visualize A plus JB as a point or a vector anywhere on this complex plane. You can have -5 minus J2, or -3 plus J5 or something like that. Any complex number that is A plus JB, you can locate a point on this plane, and you can represent a vector that starts at the origin and goes out to that point. Okay, so think about complex numbers like that. If you hadn't before, maybe you have, but you can think about complex numbers like that. They describe a point on a two-dimensional plane we call the complex plane. Okay. Now, just like on this two-dimensional, XY plot here, where you can have a polar coordinate system, you can do the same thing here. You can express a complex number as some kind of length A, or having some kind of length A, and having some angle up from the real axis, theta, right? This is just like the polar coordinate system down here. So I can express 3 plus J2 as A at an angle of theta, right? Both of these describe a point on the complex plane, which is a complex number. So you may or may not have seen this before, but this shows you that you don't have to just stick with this A plus JB to represent a complex number. You can have a magnitude, length, and an angle up from the real axis. They can both represent that vector. Okay. All right. So what does that mean, right? How let's talk about trig a little bit. How do you know how do you relate A and theta to A, little a, and little b? Well, you can do this. Let's draw another complex plane here. So here's real, here's imaginary. Let's just put a point out here, kind of like we've been doing. And then we have a vector that goes from 0 out to that point. Well, if I know that this vector has, let's say it's vector v or whatever, it's a complex number. It has some length a and angle theta. How do I relate that to a plus jb? Well, trig, right? If I want to know how far along this adjacent leg is this coordinate right here on the real axis. Well, we know the angle, we know the hypotenuse, so this is a cos theta, right? That's what this number is here from that triangle, and using a little trig. On the imaginary axis, that value there where I've drawn a dash across the imaginary axis, well, we want this leg of the triangle that is going to be j, since we're along the imaginary axis, j a sine theta, right? Okay. All right. Yeah. Someone asks why are we using j instead of I to represent complex numbers, or this complex value square root of -1? It's just because we use I to represent current. So, if I say, voltage equals 2I, do I mean, for a controlled source, do I mean imaginary, or do I mean current? So we use J. So when you see J, think square root of -1, you can actually put your calculator into a setting where it shows all complex values as J's instead of I's. It's that common. Okay. All right. So right here, I'm showing how to relate A at an angle of theta, polar, to the Cartesian values along the real and imaginary axis. Okay, so I could write this. I could write A at an angle of theta equals A cos theta, right? It's the x part plus the y part, J A sine theta. Right? Those both sides of this equal sign represent the same point on this complex plane, right? These are equal. So this is also how you transform between polar and Cartesian. Okay. Let me write this again, this expression. So this point is described by A cos theta plus J A sine theta. That describes that point right there, or that vector. Well, if you recall this from, I'm sure, one of your classes at some point, you would recognize this as the one side of Euler's formula. Remember Euler? And Euler says that A cosine theta plus J A sine theta is A e to the J theta, right? So this is Euler right here. That's Euler's formula. All right. So we have three ways now to express this value, this complex value, which can be visualized on the complex plane. We have, let me just say this here, this is Cartesian or rectangular, right? It's just x plus y, or real plus imaginary. Okay? We have polar. Right? That's polar right there. And now we have exponential. Okay, this is a way to express that same value. A, the length of that vector, times e to the j, the angle of that vector, right, using Euler's formula. We're going to use all three forms, you'll see. But I wanted to show you this is a way to visualize the relationship between polar, Cartesian, and exponential, because they all represent that point or that vector on the complex plane. Okay. So whenever you see a complex number in this class, in any form, right? 2e to the j, something in radians, or 1 plus j2, or 5 at an angle of 30 degrees, right? Whenever you have a complex number, I think it helps to visualize that number on the complex plane to know what you're working with. Okay, we'll do a little more with that. All right. Okay. We are going to call this vector a phasor. So a phasor represents the amplitude and the phase of a cosine. And I'm going to show you how that works, because this is a little weird. We have a complex number times a sine here and a real number times a cosine. But I'm going to show you how we can represent a cosine omega t plus theta using a vector on the complex plane, starting at the origin, going out to a point. But when one of these vectors represents a cosine, we call it a phasor. It's just the name we give it. Okay. So when I say phasor, think vector. Think two-dimensional vector. And when you think phasor, think complex number. Okay. So that's where we're going. And it's kind of the right second or third grade through Euler on a slide. So let me bring you back to a slide, and then we can talk about how we actually represent the amplitude and the phase of a cosine using phasors. Okay. Okay, so Euler's identity, actually Euler's formula, is this. I have swapped out the theta. I have inserted a phi here because I'm going to do a replacement. I'm going to use theta to mean phase and not angle. So phi here, this is an angle. So visualize, go back to that slide in your head or that whiteboard in your head. Um, phi here is the angle between the horizontal axis and that phasor, okay, or that vector. A is the length of that vector, okay? And here's Euler's formula saying these are equivalent. We talked about the complex plane. Here's A, here's phi, here's the relationship between A and phi, polar, and the Cartesian values. Okay, so keep that in your head. Now let me show you how to relate the amplitude and the phase of a sinusoid to these values that make up a phasor. Okay, so that phasor represents the amplitude and the phase of a sinusoid. I keep saying that over and over again because it's not intuitive. And here's what that means. That means that A e to the j theta, right, or A plus JB, represents A cosine omega t plus theta. Okay, remember, omega is a frequency. We're going to leave that aside for now. Don't worry about that. We're just going to represent the amplitude A and the phase theta with this value here. Now, I hope you can see now from that last whiteboard drawing, I hope you can visualize A plus JB means a point on the complex plane, and it represents a vector from the origin to that point. I hope you can also see A e to the j theta is a vector, a phasor that starts at the origin, goes to some point, and that point is A away from the origin and is angle theta up from the horizontal axis or real axis. Okay, so whenever you see that, visualize that. But I'm going to show you how does this represent this? We have this complex number in here and there's no complex number over here. So how is that? Well, I'm going to show you next how the phasor value, this complex number, relates to the sinusoid. But I will disclose this. I'll disclose that for this intro level circuits class, it's really more important to know how to use phasors. Okay, it's more important to be able to do calculations and use these phasors for circuit problems than it is to have a complete understanding of the derivation and the origin. So I'm going to show this to you because in the past I have neglected to show this in class, and inevitably at the end someone says, well, how do you get there? How do you get to that relationship between phasors and the sinusoid? Well, I'm going to show that. So I'm going to walk you through this, but again, you will have seen it and I think it'll make more sense later, but I want to show you this up front. This is where we started. We said, okay, this value, AE to the J phi, that's the angle up from the real axis, by Euler's formula is this. Okay, here's the real part, here's the imaginary part. Whatever I do to one side of this equation, I can do to the other. And so here's where I'm trying to end up. I'm trying to end up where I have a cosine omega t plus theta, I have this up here, equals something that includes a phasor. So we will get there. But let's start here. Let's start with this equality. And whatever I do to one side, I can do to the other. Let me just take the real part of both sides, right? That means take the imaginary part and cross it out. Just look at the real value along the real axis. Okay, so I'm just going to do that to both sides here. Okay, so the real part of the right side means, well, cross out this JA sine phi. Just cross it out because we're taking the real part of both sides. Right. On the left side, I still have the real part of AE to the J phi. On the right side, I have A cosine phi. We're getting closer to like A cosine omega t plus theta. Okay, so let me flip this around, just left to right, right to left. I have this. Now I want a cosine omega t plus theta equals something. So what I'm going to do is I'm going to say, well, just replace it. Let the angle equal omega t plus theta. Okay, so let's do that. Let's substitute that in. So you have a cosine omega t plus theta, right there, equals the real part of a e to the j. This was phi, now it's omega t plus theta. Okay, so let me write that again. There it is. Okay, when you have this sum in the exponent here, this is really a e to the j omega t plus j theta. Right? I can break that out into a product. I can say, well, this is really a e to the j theta times e to the j omega t, right? If you multiply these together, you get omega t plus theta times j, right? That's all I did. And on the left side, you have what we're looking for. This is how we defined a sinusoid, right? And this is why we use a cosine, not a sine, because you get a cosine here. Okay, so here we have one term that represents the amplitude, right, A, of that cosine and the phase of that cosine. We have another term here that has the frequency in it. Don't worry about that because our circuits are going to have sources of all the same frequency. We'll work with this later, but this term right here, this term is the phasor. That contains all of the information of the amplitude and the phase of this sinusoid. Okay, so the amplitude and the phase of a sinusoid can be represented with this value, this phasor right here. Okay, so I'll say I like to call this so this is the time domain, and I'll say this is the phasor domain. I'll often call it the phasor form of the sinusoid. So on the left, this is just the sinusoid. On the right, for exponential, polar, and rectangular, right, you can visualize that now. These are the forms. So the exponential form is this, what we just showed. That's the phasor that represents the amplitude and the phase of this cosine. But now, if you remember right from the whiteboard, you can also express a e to the j theta as just a at an angle of theta. That's polar form. Okay. And you know that if you draw the dotted lines down to the axes, right down and across to the real and imaginary axes, you can figure out what A is and what B is. Right? So these are the four ways to represent the phasors. Okay. All right. Oop, I shut that off here. Okay, so let's talk about when you do math operations on phasors, what does that do to the other side of the equation? Or conversely, right? If you do math operations like multiply by a constant or take a derivative of a cosine, how does that affect the phasor value? Because remember, in circuits, like forget about phasors, go back to what you've been doing up until now. You've been multiplying by constants. You've been V equals IR. Right? The current is multiplied by a constant R. Or you've been taking a derivative. I is equal to C dV dt. So we have to handle multiplying by constants and taking derivatives. Well, multiplying a time domain sinusoid by a constant is actually equivalent to multiplying the corresponding phasor by a constant. So if I multiply left and right side of this equation by k, I can take the k inside the real operator here, and the phasor just gets bigger by factor k. So you make a cosine bigger by multiplying by k, or smaller. You make the phasor bigger or smaller by k. Okay, so that's how you handle multiplication by constant. If you add time domain sinusoids and maybe multiply by a scaling factor, that's equivalent to adding phasors and multiplying multiplying by those scaling factors. So if I say, I'm going to take this cosine and add it to this cosine, and maybe I'll scale that by A1 and A2. Okay. Then it's just like adding together the phasors. So if you add cosines in the time domain, you can equivalently add phasors in their phasor forms. When you take a derivative, right, as we do with capacitors and inductors, if you take the derivative of the time domain cosine, that's like multiplying the phasor by j omega, right? Well, why is that? Well, if you take the derivative of this with respect to time, right, j omega comes out of this, right? This here, this phasor is a constant. It's just a number. So when you take the derivative, that just comes out in front of the derivative. If you take the derivative of e to the j omega t, j omega has to come out. So that's why this j omega shows up here. So what you're going to see is that when we look at the, we'll get there, impedance of a capacitor and an inductor, you're going to see this j omega term. And that j omega term shows up because the relationship between voltage and current has a derivative in it. Okay. Okay. So put that in your mind. It's more important to just know that we're going to be able to do this and then do what we're going to do to solve problems, then understand this completely. But this is the basis for what we're going to do. Okay. So what I want to do now is I'm going to show you an example. I'm going to do a fairly straightforward example, a graphical example, where we're going to add two sinusoids, and we're going to use phasors to do that. Okay, so let's get rid of this third grade math to Euler. And let's use phasors in an example to add two sinusoids. All right. So let's say we have a voltage sinusoid, V1 of t. And that sinusoid is 20 cosine omega t minus 45 degrees. And let me define another cosine, or another sinusoid, I should say. And I'm actually going to make this a sine function, 10 sine omega t plus 60 degrees. Okay. Now I've broken two rules here. One rule is that I'm mixing units. I have omega t, that's radians per second times seconds, that's going to be radians. And I'm subtracting degrees. You cannot do that when you're actually doing calculations. But we break this rule all the time just to be able to visualize where this phasor is or what the phase of that cosine is, right? Because you could probably visualize the angle 45 degrees, right? If I say visualize 45 degrees or visualize 30 degrees or visualize 60 degrees, you could probably do it. If I say visualize half a radian, right? Or visualize, you know, 2 radians. Can you visualize that? I can't. I'd love to know how you do that. Maybe you've memorized it. But it's easier to visualize these angles if they're in degrees. When you actually do calculations, you have to convert either omega t to degrees, right? Or more often, 45 degrees is converted to radians. That's the first rule I broke here. The second rule I broke is I said all sinusoids in this class will be represented by cosines, and I threw a sine in here. But I'm going to show you, we're going to convert that sine to a cosine. Okay. So what we want to do, we want to find the sum. Let's call that V3 of t. And that sum is V1 of t plus V2 of t. And I want that sum, I want that to be a time domain function. I want it to look like something here, right? I want it to be a sine or a cosine. It's going to be a cosine. And the way we're going to do this is we're going to use phasors. And like I said on that slide, the previous slide, if you add two phasors, I'm sorry, strike that. If you add two sinusoids in the time domain, you can equivalently just add the phasors in phasor form. So I'm not going to try this. I'm going to do this. I'm going to say V3 phasor. When I underline, I mean phasor here. Okay, so V3 phasor is V1 phasor plus V2 phasor. And let me correct that. I don't mean just phasor. I mean in general a complex number. So if you see an underline under a variable, that's a complex number in general. It might only have a real part. And you'll see when I get to impedance, I'm going to underline impedance values, but those are not phasors. So instead of trying to do this time domain calculation, I'm going to convert V1 to a phasor, convert V2 to a phasor. I'm going to add the phasors. I'm going to get V3 phasor, and then I'm going to convert V3 phasor back to the time domain. Okay. Okay. So someone asked, wait, I thought the underline also meant vectors. Yeah, that's right. So remember, a phasor is a vector, right? So yes, these are vectors that represent the amplitude and phase of a sinusoid. So instead of saying a vector that represents the amplitude and phase of a sinusoid, I'm just going to call that a phasor. So these are phasors. Okay, what is V1 phasor? Let's convert this sinusoid, 20 cos omega t minus 45 degrees, to a phasor. Okay, uh, that's easy. This phasor, this vector, has the length equal to the amplitude of the cosine it represents. It's length 20. It has the angle up from the real axis. It has the angle, in this case, negative 45 degrees. So this is 20 at an angle of negative 45 degrees. That's it. That's the phasor that represents V1. And you could say units of volts since it's a voltage. Okay. So you just take the amplitude. The amplitude of the cosine is the magnitude of the phasor. The phase of the cosine is the angle of the phasor. Okay, let's convert V2. Well, V2 is kind of funny because we didn't use a sine, we used a cosine, right? So we need a cosine here. We can't use a sine because we didn't derive phasors using sines. We derived phasors using cosines. So what I have to do is I have to say, well, how do I convert sine to a cosine? Well, sine, I'm going to use another angle here, phi is equal to cosine phi minus 90 degrees. Okay, that's equivalent. So what I can do is I can say, well, V2 of t equals 10 cos omega t. Let's see, omega t plus 60. Right? Phi here is omega t plus 60 minus 90 degrees. So V2 of t is actually 10 cos omega t minus 30 degrees. Right? So I've converted V2 to a cosine form. And now I can convert V2 of t in that form to a phasor. V2 phasor equals the length of that phasor, the magnitude of that phasor, is equal to the amplitude of the cosine, 10. The angle of the phasor is the phase of the cosine, minus 30 degrees, right? Volts. So these are the two phasors here. This is phasor V1. This is phasor V2. And now we're going to add those together. And so you could visualize this now. You're going to be adding two vectors together. Has length 20, angle minus 45 degrees. Length 10, angle minus 30 degrees. And so what I'm going to do is I'm going to, let's draw these out. Let's draw these phasors on the complex plane. I'm going to skew the origin to the upper left here because we're working in the lower right quadrant, right? So this is the real axis. This is the imaginary axis. I'm just working in this quadrant, so I've skewed the origin up here. Okay, so visualize V1. V1, I could do this. It's supposed to be an arrow. V1 has length 20 and it has an angle of 45 degrees down from the real axis. Okay, I'm not going up because it's a negative value. If it were positive 45 degrees, I'd be up in this quadrant up here. It's negative 45 degrees, so I'm below that axis. Okay. And so you can figure out the real and imaginary components. Right? So if you take 20, multiply by cosine 45, negative 45 degrees, you'll see this is 14.14. Okay. And if you take 20 and multiply it by sine, negative 45 degrees, you get negative J 14.14. That's this value here. Okay, so that's one of the vectors we're going to be adding. And then let's draw V2. This is real, this is imaginary. And so here we have, just draw it. It's not to scale. Length 10, angle minus 30 degrees. And so you could figure out with the real and imaginary parts, we're going to use these later. The real part is 10 times cosine negative 30. You get 8.66. Then 10 times sine negative 30, you get minus J5. Okay. So this point here, this phasor is 8.66 minus J5, or 10 at an angle of minus 30. That's V2. And V1 is 20 at an angle of negative 45 degrees, or equivalently 14.14 minus J 14.14. Okay. So I think now you can see where we're going here, and we'll finish this next time, but you can see we're going to add this phasor plus this phasor. If you want to call it a vector, we're going to add this vector plus this vector. We're going to get a resultant. That resultant is going to be V3. And then we're going to convert V3 back into the time domain. Okay. But what we'll do is we'll leave that. We'll finish that up next time. Okay. All right. So in closing, check out the pre-lab. It is listed up there and due this week. You'll perform lab this week. That will be Friday. See the Slack workspace. So if you have any questions about homework or anything you want, I get alerts from the Slack workspace. So that's the best way to get a hold of me for technical problems or any issues. If you have something you need to discuss privately, email is fine. But if it's some kind of technical issue with a problem, post that to Slack. Thanks for joining class. I will start office hours in just a few seconds. So if you would like to join, please join. If not, I'll see you next time. Have a great night.